I think last time we had worked on, what, worksheets 1 and 2, right? So let's start in with that. Landon, what do you want to start with?
So for the worksheet 4, could you do number 11?
Sure. Let me grab that. And I'm going to drop in the unit circle here because I'm going to be using that to do these problems. So it just helps to have it to reference. Okay, and you said number 11?
Yeah.
Okay. So first thing I'll do is I'm going to use that interval from 3 pi to 4 pi to figure out what two quadrants we're looking in. So we have 0, pi over 2, pi, 3 pi over 2, 2 pi, 5 pi over 2, 3 pi, 7 pi over 2, and then 4 pi. So we're going to be looking in quadrants 3 and 4. Now, I'm also going to use my all silly turtles crawl to figure out what quadrant tangent is positive in. Well, that is quadrant 3. So my theta then goes around 1 full time and then to the terminal side. Everybody feel okay with what we did there so far? So what I'm going to do then is I'm going to go to my unit circle and I'm going to find out the place where tangent is equal to root 3 over 3. Remember that tangent is y over x on the unit circle. So I'm going to be looking for the place where the y-coordinate is root 3 and the x-coordinate is positive 3. But that's not really going to be very helpful because there is no like regular 3's on the unit circle anyway. So I'm going to think to myself, well, I can think about regular 3 as root 3 times root 3. So I could reduce this to 1 over root 3 and then go to the unit circle and look for a place where the y-coordinate has a 1 in it and a place where the x-coordinate has a root 3 in it. So that's what I'm going to do. So quadrant 3, the y-coordinate needs to have a 1 in it and the x-coordinate needs to have a root 3 in it. So I'm looking at 7 pi over 6. So far, so good?
Yeah.
Okay, we got a little bit more to do, though. Welcome. So remember, when we drew our picture here, notice that we went around the unit circle 1 full time before we went to the terminal side. So that means that I'm going to be having to add 1 full rotation to this answer. So to do that, I'm going to make like a common denominator. So I'm going to be adding 12 pi plus 7 pi to give me 19 pi. And then when we add fractions, the denominator just stays the same, and that's the final answer. Does that feel okay there, Landon?
Yeah.
So the trickiest piece was probably this spot right here, and like, oh, I need to reduce that in order to kind of see what the x and y are supposed to be.
Yeah.
And that's probably not a trick that you'd come up with on your own. But now having seen it, be like, oh yeah, okay, if that happens again, I know what to do. Maybe. At least you've seen what to do. Know it's something you can do. Who else? Do we want to talk about some more of these? I imagine we probably do. Some of these were rather difficult. Maybe not from worksheet 1, but worksheet 2, I think there was several things that were kind of tricky.
Could you go over and check it again?
Sure, I'd be happy to do that. So there's two things that I'm going to want to check. One thing, I'm going to want to make sure my mode is in radian mode. So right now I'm not. So I start by just pressing the mode button right next to the second. And I want to change that to radian mode. So first thing I'm going to do is I'm going to plug this angle in for theta and make sure I get this value. So I'm going to do tan of 19 pi over 6. It gives me that decimal. Well, I don't know if that's root 3 over 3, but to figure that out, I'll just do root 3 over 3 on my calculator and make sure they're the same decimal. So they are, so that's good. So that's the first half of my check. The second half is I want to make sure that 19 pi over 6 is bigger than 3 pi and less than 4 pi. So 3 pi is that. 19 pi over 6 is bigger. And 4 pi is bigger than that, so I'm good. I'm satisfied that this answer is correct. Is that okay?
Yeah.
Which is nice, right? Having a way to check this even without an answer key. Yeah. Who else? Happy to do more if you're interested. Victoria, Jeepers Creepers. Yeah, of course. Had a little like senior moment there and couldn't remember. Somehow wasn't remembering a name, which is kind of embarrassing. All right, let's do that. Worksheet 2, number 2. Okay. So I'm going to start by drawing a picture to figure out, using that range of values, what two quadrants we're working in. So 0, pi over 2, pi, 3 pi over 2, 2 pi, 5 pi over 2, 3 pi. So we're looking at quadrants 1 and 2. Then I'm going to use all silly turtles crawl and figure out what quadrant cosine is positive in. Well, that's going to be quadrant 1. Is that okay? All right. And so I know I'm going to go around one full time before I get there, so that's my theta. And then my alpha is going to be the acute angle formed by the terminal side and the x-axis. And since the last axis that theta passed through was a horizontal, that tells me that I'm going to be adding alpha. So theta is going to equal the last value on my x-axis that I passed through plus alpha. And alpha is always the inverse of the absolute value. And now it's calculator time. So 2 pi plus cosine inverse, and I'm just going to do the absolute value in my head. There's really nothing to do there. And I get 726-ish. And just as Landon asked, let's check this once real quick. So to do that, I'm going to do cosine of that value and make sure it gives me 0.56, which it did, so that's good. And then I want to check to make sure that 726 is in between 2 pi and 3 pi. So it's definitely bigger than 2 pi and smaller than 3 pi, so I'm satisfied that this answer is correct. Does that work for you, Victoria? Of course. What do you guys think? Landon? On which worksheet? Sure. Okay. So again, I'm going to start by drawing my picture to figure out where my theta lies. Notice this time when I'm given the range of values that the theta is a negative value, right? Because we're between negative 4 pi and negative 3 pi. So when I'm going and drawing my picture, I'm remembering to go clockwise around instead of counterclockwise. So 0, negative pi over 2, negative pi, negative 3 pi over 2, negative 2 pi, negative 5 pi over 2, negative 3 pi, negative 7 pi over 2, negative 4 pi. So we're looking at quadrants 1 and 2. And then where is tangent positive between quadrants 1 and 2? Quadrant 1, right? Using all silly turtles crawl. So there's my theta. Now remember, when I'm drawing this, I'm going clockwise instead of counterclockwise because we're using theta as a negative value. So I go around 1 full time and then onto my terminal side. So that's my theta. Now, since theta is a negative number, I know that my rules for adding and subtracting alpha are opposite, right? Normally, if the last value I'm passing through is, or the last axis I'm passing through is vertical, I'd be subtracting. But since alpha is negative, it's actually adding. So theta is going to be, and then again, obviously, this is my alpha. Always terminal with the x-axis, the acute angle. Is going to be negative 4 pi plus alpha, where the alpha is, again, the absolute value of the inverse. So that's a negative 1107. Oops. And again, to check this, we can do tangent of that value. And that should give us 1295, which it did. And then I'd want to check that that number is bigger than negative 4 pi, which it is, and smaller than negative 3 pi, which it also is. So we're good. So the tricky part on that one was the negative thetas meant we had to kind of reverse everything that we typically do. But it was, aside from that, it was still, the process was just identical. We had to just make that one modification because of the negative. Okay. What do you guys think? Is it getting there?
It's hard to remember.
Sure. I will say that of the skills from this chapter, this is the big one kind of moving forward that we want to make sure that we have well in hand. When we talk about solving trigonometric equations later on this semester, if we can't do this part of it, it's going to be really difficult to solve a trigonometric equation. If we can't then use this process to kind of find our answers. So this is a place where this skill comes back in a big way. So we want to make sure that we're able to do this, okay? So that being said, I'm going to do a little bit more to finish up section 4.1, and then we'll just give you some time in class to continue to kind of work on this stuff where you can get some immediate feedback. Sound fair?
Yeah.
Okay. Let's do that. So there's not a whole lot left in 4.1 to do. I'm basically just going to be looking at kind of a couple of example problems, okay? And then we have to talk a little bit about notation. Let's do the notation part first, actually. So last time we defined these three inverse functions: sine inverse, cosine inverse, and tan inverse. And this was the notation that we used to kind of describe them, was we used this old -1. Now there's another older notation that's still used, maybe not commonly, but not infrequently either. So that older notation is just using the prefix arc. Actually, let's do that and put the f of x there. So if we talk about arc sine or arc cosine or arctan, we're really talking about the same thing as tan inverse, sine inverse, cosine inverse. So it's just another notation. Again, this is not uncommon in mathematics to have like several notations to describe the same thing. The reason that is often is that these ideas were developed kind of in parallel with each other in different regions prior to communication being easy. So you'd have like, for hundreds of years, like people in Eastern Europe use one notation, the people in Western Europe are using a different notation because there's no journals or easy communication or like published documents that get traded back and forth. Like you end up with these two different notations that are both kind of cemented. You know, I have like hundreds of years of legacy of doing it using this notation. And then they both kind of get married into, you know, modern notation. So neither one of them seems willing to go away. Now in America, we probably see the symbols on the left more often than not, but would not be uncommon to see the arcs in there. And I think that will show up in the problem set here a little bit. So just wanted to get that through. Everybody okay with that? No big deal, but if you don't say what it is, then you look at it and you're like, what the devil is this, right? Okay. So let's say that we have this problem. Where we're going to take arctangent of tangent of 5 pi over 4. Now, the natural inclination would be to say, okay, well, I'm doing tangent inverse of tangent. So these two things should just cancel out. And I should be left with 5 pi over 4, right? Unfortunately, that's not going to be what happens here. The reason that doesn't happen, so remember for tan inverse, the range of values was negative pi over 2 to positive pi over 2. And if we look, 5 pi over 4 is definitely not in that interval, right? So there's no way that tan inverse should be giving us 5 pi over 4. That's why that answer is incorrect and why we can't just cancel those things out all willy-nilly. Is that okay? So what should we do instead? Well, instead what we're going to do is we're going to work from the inside out. So I'm going to go ahead and evaluate tangent of 5 pi over 4 using the unit circle. When I do that, I get negative root 2 over 2 divided by negative root 2 over 2. Oops. Which is really just 1. Everybody's okay with that? Now, if I'm going to do arctan of 1, I remember that the range for arctangent, or tangent inverse, is negative pi over 2 to positive pi over 2. So if I draw my picture here, we're talking about quadrants 1 and 4. Everybody's okay with that? And the place in quadrants 1 and 4 where tangent is positive is quadrant 1. So really we're looking for that value. Everybody's okay with that? So again, I'm going to go to the unit circle, and I'm going to look for the place where y over x gives me 1. That's basically going to be the place where the x and y coordinates are the same. So I think I have that already in here from before. Where are my unit circle? There you are. So looking in quadrant 1, the place where the x and y coordinate are the same is here at pi over 4. Everybody's okay there? And that should be my answer. We okay with that? Okay. So again, not terribly difficult, right? But it's one of those things like if nobody reminds you that, hey, you have to be cognizant of the range of this inverse, the impulse would be to just cancel things out all willy-nilly and it's no big deal. Okay. And then the last thing that I want to talk about in this section 4.1 is another example. So let's say here we have this example. It says find an algebraic expression equivalent to sine of arc cosine of 2x. So the trick on this kind of a problem is, again, to work from the inside out. So we're going to start with the arc cosine of 2x. And I know that if I'm doing like an arc cosine or a cosine inverse or a sine inverse or whatever, that's giving us an angle measure. Everybody's okay with that? Okay. So, oops, 2x. And I know that this then, theta equals arc cosine of 2x, is equivalent to just cosine theta equals 2x, right? We good there? And using that, I'm going to go back and use my right triangle definition. So I remember that cosine is adjacent over hypotenuse. So I'm going to draw myself a right triangle. Label one of those angles as theta. The side adjacent to theta is going to be 2x. And then the hypotenuse is going to be 1. Everybody's okay with what I've done so far? So what I can really do now is this problem just becomes sine of theta that I'm going to be evaluating in the triangle that I've drawn below. So using my right triangle definition for sine, I know that's opposite over hypotenuse. The one little catch is I don't know the opposite side. Right? If I look at my right triangle that I've drawn, we don't have the opposite side. But we have two sides in a right triangle, right? We should be able to solve for that third side. What would we need to use to solve for that third side? If I have two sides in a right triangle, what can I use to find the third side? You've used it many, many times in your life. Lily? That's what I was looking for. Yes, the Pythagorean Theorem. So I'm going to label this opposite side just A. So using the Pythagorean Theorem, I know that A squared plus 2x squared is equal to 1 squared. Remember, if you have ax squared plus bx squared plus c squared, the c has to be the hypotenuse, right? That's the only catch about the Pythagorean Theorem. Okay. 2x squared is 2x times 2x, so that would be 4x squared. And 1 squared is just 1. And then we'll subtract 4x squared from both sides. And then we'll square root both sides. Everybody so far so good? Notice that I dropped the plus or minus that I would normally put on there for square rooting both sides. Why was I able to just drop the plus or minus and assume that this is positive? What is A describing? Tyler?
It's describing distance, and you can't have negative distance.
Perfect, yes. A is describing a side length on a right triangle. That's a length or a distance. Certainly you can't have negative side lengths on a triangle, so I can just straight assume that this is going to be positive. I don't have to worry about the negative for the plus or minus. Is that okay with everybody? Okay. Can I simplify the square root of 1 minus 4x squared anymore? I mean, can I just call this like square root of 1 minus square root of 4x squared? What do you think? Can I do that? Square root of the 1, square root of the 4, square root of the x squared. Just call it that. What do you think?
Sure.
No!
No.
Why is the reason I can't do that? It's because of the addition or subtraction going on underneath the square root. So you can break a square root at multiplication, like I had done there, but you can't break a square root at addition or subtraction, like we were trying to do there. So if you have addition or subtraction under your square root, there's basically nothing you're going to be able to do, or not much you're going to be able to do. Okay? Okay. So that's my A. So now sine theta is going to be opposite, which is my A, over hypotenuse, which is my 1. So I'm just going to have root 1 minus 4x squared divided by 1. And obviously anything over 1 is just itself. So there's my algebraic expression. Okie dokie. Oh. Okay, that's where I want to stop. So you guys have been working on worksheets 1 and 2. I'm going to add on the problems 1 through 18. And then we're going to take the rest of our time here in class to work on the worksheets and or the problem set, kind of whichever one, wherever you're at, everybody should have something to be working on. Okay?